Okay, so this is one of the demonstrations we put together last year in the freshman seminar on the engineering of trees. And it was set up to demonstrate column buckling. And most people have some idea about column buckling. If you take a column like this and you start to compress it between your hands, not much happens at first. It actually will get a teeny bit shorter, but not too much happens. And then when you get to some critical load, it'll buckle out like that. So that's what column buckling is. And in the seminar, one of the things we talked about was how the height of the tree relative to the diameter was controlled by column buckling. So we wanted a demonstration to kind of show how this works. There's something called the Euler formula, the Euler equation, which gives you the critical buckling load for column buckling. And the Euler load depends really on three things. One is the stiffness of the material. The stiffer the material is, the larger the buckling load. Depends on the diameter of the column. The larger the diameter, the larger the load. And it depends on the length of the column. The larger the length, the lower the load. So as the column gets taller, it gets easier to buckle the column. So this particular demonstration here is set up with three columns all made of the same material, so they all have the same stiffness. They all have the same length, so they're all the same height, 18 inches here, but they're three different diameters. So this one here is 3/16 inch, that's a quarter, 4/16 inch, and that's 5/16 of an inch. So they're different diameters. And this is set up so that this lever then moves some pistons in the back of the demonstration, and that moves each of these top platens down. And as I put load into this bucket here, what happens is initially the skinniest column buckles out first, so you can see the 3/16 inch column is buckling. And then as I put more load in, this quarter-inch column will start to buckle. So here we're showing really that the diameter has an effect on the buckling load, and the smaller the diameter, the lower the buckling load. So if I do that again, here's our skinniest column. It's just about to go. There we go. So that column is buckling out, and you can see it moving out sideways. If we now look at the next skinniest column, the quarter-inch one, as I put more load there, it just goes there, and you can just see it start to buckle out. So this one buckles less than the thinner one, but you can still see there's some buckling out. And we've designed this so that the thickest column, the 5/16 inch column, doesn't buckle at all under the loads that we can impose with this particular setup. We also have a set of beams of three different materials, so one's steel, one's aluminum, one's wood, and you can put three different materials of the same diameter and the same length in, and the wood one goes first, and then the aluminum one, and then the steel one. We have another setup where we have different heights here for the columns, so the height of these three devices is different. We have a 24-inch column, an 18-inch column, and a 12-inch column, and you can see that the longer one buckles first, and then the second longest, and then the last one actually doesn't buckle at all. So that's really all there is to this demonstration, just showing the buckling load and how it varies with these different parameters, and then how that relates to this Euler critical buckling load for column buckling.